Let's have a look at the chip where everything is happening. Our chip has a gold nanohole array structure. When illuminated with a light source, a plasmon gets excited at the surface and re-emits light in transmission. As you can see on this picture, we also use gold nanoparticle. When one of these particles is close to the surface, it strongly and locally affects the plasmon excitation, and so the intensity of the transmitted light is reduced at this precise location. To take advantage of this effect, we create a one-step sandwich assay. The capture antibody are beforehand spotted on the gold surface, and a solution containing the plasma with adalimumab and our gold nanoparticle coated with our detection antibody is directly applied on the chip. Then, the adalimumab binds to the gold nanoparticle, and this complex will bind to the surface. With this sandwich configuration, the transmitted light is reduced at those precise locations where the gold nanoparticle is. And so, by illuminating from the top and putting a camera at the bottom, we can see black dot on the image, which correspond to the binding event. So basically, we can detect a single binding event, and furthermore, the total amount of binding event is directly linked to the sample concentration. Thanks to this, our technique is very sensitive and rapidly gets a signal. Then, since we spot the capture antibody on the surface, we can spot different capture antibody on the same chip and so create a multiplex assay. And then, our technique only requires to mix the gold nanoparticle with the plasma and directly apply it on the chip, which makes it an easy-to-use method. So, this is one of the images we got. As you can see, the signal is very clear. We can easily distinguish the black dots that corresponding to the binding event. And furthermore, we can also easily distinguish the figure of the capture antibody spot. Our algorithm digitally counts the number of binding events and plot the evolution over time. Then, by fitting a biokinetic model on the event evolution, we extract the sample concentration. But now, let's have a look to our optical system. As you can see, it's very simple. What do we have? A light source, an objective, and a camera. That's it. This system is directly connected to a touchscreen with which the user can interact. Then, the user just have to insert the chip in the device, which will give the result and display it on the screen. So overall, with our simple and innovative device, we offer Swiss precision in service of healthcare improvement. Thank you for your attention.
So, are there any questions? Yes?
So I have two questions, very interesting talk and concept. So the first one is, so you incubate your particles, gold particles with the serum, and then you place the serum on the chip as is. So what is the wavelength of light you use for the transmission measurements?
It's a 660 nanometer.
Okay, 660 nanometers. So you don't get much interference from serum at that wavelength?
No, we didn't get it.
And so the second question was about the about the spot counting. So how do you count the spots?
We basically make a simple image processing, and then we make a threshold of the image with the black dots will be black, and all the other stuff will be white. And then you can say, okay, but there will be dust that will be also black. So what we do is we put a size filter, and so after that we count only the particles that have the good size. So it's the good intensity and the good size.
Okay, thank you. Oops.
So is it that you see per dot one molecular event?
Yeah.
Yeah.
Yeah, it is.
So the concentration you just have shown in this plot, this must be very low then, right? So
Which
what,
one?
what is the theoretical
This one?
concentration limit then?
The
So
concentration limit?
yeah, so you would see one binding event, right?
Yeah. So in fact, this technique can detect really low concentration until the picogram. But in fact, when you have to, if you have to adapt to see more concentration, you have to adapt the concentration of the gold nanoparticle, and also we have a bit this concentration that we have for the competition. We had to dilute it a bit to detect a signal.
Okay.
Thank you for a very nice presentation.
Thank you.
Looking at this picture here, I see a lot of black dots. Can you try to elaborate which black dots you're actually looking at?
So, this big circle that you see here is the capture antibody spot,
The round circle?
the round circle. And inside this round circle, you have full of small black dots. And
Yeah.
each of these black dots is a binding event.
But I also see black dots outside. the round
Exactly,
circle.
exactly. Because you see a black dot when the gold nanoparticle is close to the surface.
Yeah.
So by diffusion, of course, you will have sometimes some gold nanoparticle that will be close to the surface. It will come close and then move away. And that's really useful because we use this as a reference for our spot.
Okay, so the signal to noise ratio is actually calculated on your background outside the circle with estimated compared to inside the circle. So that's clever, using that as a signal to noise ratio. So any kind of, now this is gold nanoparticles that are approaching the surface. But what about other impurities? Have you thought about that? Just standard impurities, dust on the lens, or
Yeah.
small other samples, components in your sample?
Yeah, of course, we thought about that. And in fact, we use antibody that are
Yes.
available on the market and that are really, really specific to adalimumab.
Yeah.
So we expect that since it's really specific, we don't detect other particles that are in the plasma and so on.
And then related to your question, normally, so you cannot distinguish whether it's from specific interference from other samples and
You mean if there is
another affinity to aluminum? This thing that we are measuring.
adalimumab?
Yeah, exactly. That one. Hate that name. Tried 10 months to learn how to say it, and I didn't succeed. Yes.
So basically, what we do also is that we put a control spot also on the surface.
Yeah.
And this control spot is exactly for those impurities. And if you see on this image, this is the control spot.
Right. Okay.
And so you can clearly see that there is no interference.
Nice.
So, sorry, the concept, the general concept, was this developed by the team, or where does it come from?
No, the concept comes from a lab from EPFL,
Yeah.
by us,
Mhm.
and especially the PhD student Alexander Belushkin. And he creates this technique with this gold nanoparticle that disturb the plasmonic resonance. It comes from him.
Okay, well, thank you very much for your interesting presentation and technique.
Thank you.
I have a question related to the interference of the other gold nanoparticles. Do you think because as far as I understood from the technical report and when I saw you testing, you just place the droplet on the top of the...
Exactly.
Would it be better if you kind of adapt it to some microfluidics to watch it? Or did you try to do some measurements on this sense?
That's a really good question, and we totally think about that. But we didn't implement it because of time, and because of mainly because of time, and we wanted to focus to detect something and to have a result before to go in microfluidic. But that's definitely something that we will do, definitely.
Okay, good. Thank you.
small question or perhaps a remark. This is the first time that I see an assay that is truly a bridging assay, because you have the adalimumab and you need both arms of the antibody free in order to detect adalimumab. You should realize, a lot of the current commercially available assays are like this bridging assay concept. But you should realize that some patients can develop antibodies to adalimumab. If they do, you will your assay is sensitive to patients that have that kind of interference. Clinically, that doesn't have to be a problem, but it is something you should take into account. Yeah.
Okay.
Yeah. Yeah.
Okay, thank you.